I'd like to talk some more about integration by parts. To start with, you can do integrals of this type. Cosine of a constant times x times e raised to some other constant times x with respect to x, or the similar integral with sine instead of cosine. This can be done by doing integration by parts, but you have to do it twice. So to get started, I'm going to pick u to be the exponential part, and dv will be the trig part together with the dx. Derivative of u with respect to x is easy to calculate. By the chain rule, it's e raised to the 2x times derivative of 2x. So du ends up being 2e to the 2x dx. Also, dv, being what it is, says that the derivative of v with respect to x is cosine of 3x. That's easy enough to integrate. An antiderivative is 1/3 sine e to the 3x. So going back to the integration by parts formula, the integral of u dv is u times v minus integral of v du. We've figured out what u and v are, so we just write down the first part, and then we subtract away the integral of v du, which I've literally written out. Taking a constant factor of 2 and a constant factor of 1/3 out of that integral, we find out that the integral that we're after is this expression. At first glance, this doesn't seem like it's any better than what we started with, because we now need to know the integral of e to the 2x times sine of 3x, and we don't know that offhand any more than we knew the answer to the problem in the first place. To try to keep things straight, I'm going to make up a symbol to call the thing that I'm trying to calculate. I'll call the integral capital I, and what we've figured out is that capital I is equal to this expression, which I'll rewrite as 1/3 e to the 2x sine 3x minus 2/3 times, in a pair of brackets, an integral that I don't know how to do. What we'll do is, to get this integral that we don't know how to do, we'll do integration by parts again. Take the u to be the exponential, just as you did the first time around. So du is the same thing it was on the first problem. dv is going to be sine of 3x dx. Turn that into a statement about derivatives. V is an antiderivative for sine of 3x, and negative 1/3 times cosine 3x will be an antiderivative. Integral of u dv works out to be, after you put all the pieces in, negative 1/3 e to the 2x cosine of 3x plus 2/3 times this integral with the exponential function and the cosine function is the thing that I'm trying to figure out. So I just write down its abbreviation. I write down I here. Going back to the first integration by parts, within these brackets, I'm going to write down this expression that I just figured out for this other integral. It looks like this is going around in circles because in order to calculate I, apparently I would need to know what I is, but it turns out that's not true. Distribute the 2/3 across the bracket, take care of the signs, and you'll find out that I is equal to a known function plus another known function minus 4/9 times I. To make the algebra nicer, multiply through by 9. This will get rid of all the fractions for us. Once you've done that, 9i is 3e to the 2x sine 3x plus 2e to the 2x cosine 3x. minus 4 times I, add 4 times I to both sides. Over here it goes away, and 9 plus 4 is 13. 13 times the thing that I'm looking for is this known function. Divide through by the 13, and we have an antiderivative for our original problem, and we get all the other antiderivatives by adding a constant of integration, c. If you're doing an integral, and the thing that you're integrating looks like f of x times g of x, where f is a polynomial, and g is some function that's easily repeatedly integrated, then there's a table way to simplify this whole repeated integration by parts formula. So we certainly want to look at that. I want to look at the integral of 3x squared plus 5x plus 1 multiplied by e to the 2x. For my u, I'm always going to use the polynomial bit. So du dx will be 6x plus 5, and du will be 6x plus 5 dx. dv will be the rest of the integral. It'll be e to the 2x dx. The derivative of v is e to the 2x. If you integrate that, you get 1/2 e to the 2x. The original integral is the same thing as this quantity minus this integral. Now, I don't know what that integral is, but in a certain sense, it's simpler than the original integral was. There's no x squared in the polynomial. Also, I'm not going to simplify anything for reasons that will become clearer shortly. So I want to look at that remaining integral. I'm going to let u be the polynomial piece, the 6x plus 5. du dx is 6. du is 6 times dx. dv is 1/2 e to the 2x dx. When you integrate that, you pick up an additional factor of 1/2. So you now have a 1/4 times e to the 2x. Just the part that we didn't know before is 6x plus 5 times 1/4 e to the 2x minus 6 times 1/4 times e to the 2x dx. I'm going to pretend I don't actually know that integral and go on and continue this process. The quantity inside the square brackets here is what we got when we did that second integration by parts. This was the u times v from the original integration by parts. Notice that you've got minus, minus, which is why that turns into a plus. You've got the negative of this term. And I want to leave these things just as they are for reasons that'll become clear in just a second. You might want to note down these terms. I've got a recipe. I'm going to write down the polynomial piece. I'm going to start taking derivatives of it until I run out of derivatives, until they're all 0, which happens after a while. So 3x squared plus 5x plus 1 has derivative 6x plus 5, which has derivative 6, which is a constant, so its derivative is 0, and all later derivatives are 0 also. So in the polynomial column, differentiate. Write down the e to the 2x and start integrating it over and over again. I'm not doing derivatives of e to the 2x. I'm finding antiderivatives. The exponential is very nice. The 2 means that you pick up an extra factor of 1/2 every time you do this. So it's easy enough to write out these derivatives. What we're going to do is we're going to draw downward sloping lines that connect things in the first column to things in the second column. Each thing over here gets multiplied by its corresponding quantity in the second column. We're going to add the first thing and then subtract the second one and then add the third one. The reason why we add the third one is because of minus minus is plus in that integration by parts. So let's write out what we get here. If you carry out this plan, we're going to add that quantity, we're going to subtract that quantity, then we'll add that quantity. If we had more of them, we would subtract the next one and add the next one after that, and so on and so forth. And if you look at what you get when you do that, as compared to the answer that we got off of integration by parts the first way, we have the quadratic times 1/2 e to the 2x, the quadratic times 1/2 e to the 2x. We had minus 6x plus 5 times 1/4 times the exponential, minus 6x plus 5 times 1/4 times the exponential, and we added 6 times 1/8 times e to the 2x, add 6 times 1/8 times e to the 2x. That's correct. That's the answer that we got by working it out twice doing integration by parts. This is very often a convenient thing if you have a polynomial times something that's easy to integrate over and over again. As another example, think about the integral of x cubed times cosine x. X cubed is a polynomial, so eventually its derivatives are all zero. The cosine function is a very familiar function to us. We know how to repeatedly differentiate and integrate cosine. So start with x cubed, derivative is 3x squared, derivative of that is 6 times x, derivative of that is 6, and after that, the derivatives of the polynomial part are all zero. Antiderivative for cosine is sine, because the derivative of sine is cosine. A function whose derivative is the sine is negative cosine. The derivative of negative sine x is negative cosine x, and the derivative of cosine x is negative sine x. Then draw your downward sloping lines and start doing this add and subtract business. We're going to add x cubed sine x. We're going to subtract away 3x squared times the negative of cosine x. I'm being careful about my minus signs here. I'm going to add 6x times the negative of sine of x. Then I'm going to subtract 6 times cosine x, which I do here, and then simplify it with eliminating redundant negative signs. An antiderivative for x cubed cosine x with respect to x is this. It's x cubed sine x plus 3x squared cosine x minus 6x sine x minus 6 cosine x plus a constant. People will often group like terms together. For example, the terms that have sine of x in them, they would group those together and write it as x cubed minus 6x, all multiplied by sine x, and do something similar for the cosine. But as far as I'm concerned, this is a perfectly reasonable way to write the answer. So we know this about integration. We have a big collection of rules from the first semester. Given an integral to solve, the first thing I ask myself is it one of those? Or is there some reasonably simple way I can twist it around and make it look like one of those? If that answer is yes, I'm done. If the answer is no, I have to try something else. Usually, the first thing I think of trying is integration by parts. We've seen what the procedure amounts to. Sometimes you can do an integral with integration by parts, and sometimes you can't. If that doesn't work, we'll have to have some other technique to try next. But I think this gets enough of the fundamental points of integration by parts across. So I'm going to stop talking about this, and we'll talk about the next new method of integrating in the next discussion. I hope everyone's doing well. Have a good day.